A very good afternoon to all the students. I welcome you to this session of Daa, and in this session we will learn how to analyze the algorithms. So the outline for the today's PPT is, and what the student will be able to do after the learning this topic. You will be able to analyze the algorithm, the efficiency of the algorithm, average, best case and worst case analysis, asymptotic notations that we are already covering, and also the analyzing of the control statements. So what is analysis of an algorithm? The analysis of an algorithm means the calculating or predicting the resources whichever the algorithm requires. Fine, the algorithm requires so many resources like it needs time, it needs space, it needs CPU power, it needs CPU register to execute, it use network resources to run the different algorithms. So the analyzing of algorithm means calculating or predicting the resources whichever the algorithm requires. So analysis is the theoretical estimation for the required resources of an algorithm to solve a specific computational problem. That means theoretically we are telling ki this much time, this much memory is required by the algo to get executed. So two most important resources are computing time and the storage space. I already explained you time complexity and space complexity. Why analysis is required? By analyzing some of the candidate algorithms for a problem, the most efficient one can be easily identified. Now, what does this line say? Candidate algorithm means actually you have been given a problem to be solved. Fine, you have number of algorithms which can be its answer, which can be the solution for the given problems. For example, you have written 10 algorithms, which could be the potential candidates to to solve the given problem, and they are numbered from A1 to A10. Now, how will you identify which one is the best to implement the solution of that particular uh, problem? So we will analyze all the algorithms in terms of space and time complexity, and whichever the whichever the algorithm is taking less time to execute and less memory space could be the best one. So the A1 to A10, whatever the solution for the program or for the problem, there are 10 algorithms and they are called the candidate solutions and or candidate algorithms for a given problem. And one which we identify in terms of efficiency, that is, which is efficient in terms of both space and time, could be the answer for the algorithm or could be the best algorithm which could be chosen to implement as a program for the given problem. So next, so efficiency of algorithm is measure of amount of resources which are consumed in solving the problem of size n. I already told you that every problem which is designed for the generalized form. So we always take n inputs. So algorithm must be analyzed to determine its resource usage. That is how many resources is being taken by the algorithm. So the two major component resources which are taken, they are known as execution time and the memory space. So memory space is not that much of importance today because SSDs are available, flash drives are available, Google drives are available, cloud storage is available. So most of the algorithms are basically uh, analyzed in terms of time complexity. They should be efficient in terms of time. So we have two approaches. One is called empirical approach, another is called theoretical approach. Empirical approach is always used when you are running the when you have converted your algorithm into the program and you are running that program onto the computing environment, that is with the hardware and with the software and also with the operating system. So you need three computing environment is being required to run your program in the empirical approach. Then it will calculate how much processor time is being used by your program to get executed. Theoretical approach is just the guess that how much computing time will it be taking, will your algo be taking for the input size of n. Means if you are giving n inputs to your algo, how much time roughly it will take. But for verification, you have to convert that particular algo into the program and then you will run onto the computing environment and then you will see how much processing time is being needed or how much processing time is being taken by the computer to solve a given problem. So these are various differences which are there. I already told you posteriori and priori approach. So theoretical approach is priori approach. So first of all, we will have a look at the priori approach just to determine mathematically the resources needed by each algorithm. Whatever the resources which are being used by algorithm to get executed, they are determined mathematically just by applying some formulas. In theoretical approach, we always use the algorithm, so it is independent of the any programming language. So the speed of algorithm can be determined independently of any hardware and software or computing environment. Characterizes the running time as a function of input size n and consider all the possible values. We may use the permutation and combination so that we can run the algo for n cases, but using the simple uh, mathematical functions whichever are being applied on the algorithm to get executed. Now, posterior approach is something different. That is programming different computing techniques and running them on the various input using computer. See, Python is simple as compared to Java. So it may take less number of statements to get the code for a given problem. And Java will take more lines of code. So it could be difficult. So it depends upon your choice, whichever the programming language you are choosing. There are a lot of programming languages which are there in the market, and it's your comfort zone in which you are going to code for the given problem. Then implementation of different techniques may be difficult. Theoretically, it seems to be easy, but when you apply in the system, it seems to be difficult. So the hardware and the software support is also required when you are comparing two or more algorithms. See, we have mathematically we have derived there. See, there are 10 candidate solutions. We find that 5 out of it can be the best possible solutions. Out of that, when you will run all those 5 onto the computer, you will find the best one. Fine. For that, that 5 algos needs to be converted into the program code. And after converting them to the program code, they are run in the computing environment. From there, you will calculate the time and space which will be taken by each of them, and the algo which would be taking less time and less space would be the best one. So that means you know you need to have same hardware and software environment to compare the algorithms which are being designed for a single problem. So result may not be indicative of the running time on the inputs not included in the experiment. Actually, results, whatever the results you are getting, it could vary for 100 inputs to thousands to 10,000 inputs. So they are included in the experiment. Okay. So time complexity of an algorithm quantifies the amount of time which is being taken by an algorithm to run as a function of the length of input. So running time of an algorithm depends upon the input size and the nature of input. Generally, the time grows with the size of input. For example, if we say if we are going to sort 100 numbers, it will take less amount of time. And if we are sorting crores or billions of numbers, it may take more time. So that means the time will grow as the input size will increase. So time is usually a function of the given input size. Instead of measuring actually what time is taken by the each statement in the code, we actually measure how many times each statement of that code is executed. For example, for you are calculating the sum of n numbers. If I write for I is equal to 0, I less than n, and I plus plus, I write sum is equal to sum plus ai. That means that my loop is running for n plus 1 times. Why n plus 1 times? Because I am starting it from 1, I'm going to less than n, that is okay. And for making loop false, it will execute one more time. So that means it is executing n plus 1 times. Fine. And the statement which is inside it, that is sum is equal to sum plus ai, that will get executed for the n times, because at n plus 1 time, the loop will become false. So that means we have to measure that how many times the each statement of code is executed. Then after that, we also see the number of computations which are involved in each step, whether they are scientific, whether they are primitive, whatever the operations we are performing, that also takes some time to get executed. So running time also takes the number of primitive operations which are to be performed, or what or different computations which we are performing inside the instruction. So problem and instance. See, what is problem and what is instance? The instance is snippet of the problem. That is, the input which is needed to compute the solution of the problem is the instance. For example, the problem is to multiply two positive numbers, but when you give the specific numbers to multiply, it becomes the instance. Okay, now what is instance size? Any integer that is some way measures the number of components in the instance. What would be the number of components in the instance? That is usually measured, and it is called instance size. For sorting problems, if we are sorting any numbers, that means whatever the size of array you are giving, or the number of elements you are giving in an array to get sorted, is called instance size. Similarly, in graph problem, you are given number of edges and number of nodes. So when you count the number of nodes or number of edges which are being given to you, or both you may count, so that will be your instance size. That means you have to solve the problem for this particular instance. Then is the linear search. See, I already told you that there is a box or a jar which contains some business cards, and I want to search the name Bill Gates in the jar. To do this, we have to simply go through all cards one by one, and how long this will take, it could be determined by how many cards are there in the jar. And it depends on the size of the input. Right? And linear search is a method to find a particular value from the given list, and it checks each element one at a time and in a sequence. That means it will check the element one by one in a sequence until the desired element is found. So linear search is the simplest search algorithm, and it is special case of brute force search. Brute force search means hit and trial search. Direct search, you can say, or simplest form of search is brute force search. Suppose I'll search for 1 in the given array. 29318 is the given numbers, and we have the index from 1, 2, 3, 4. Fine. So 29318 are positioned at 1, 2, 3, 4, and 5 indexes. For first index is 1, for I is equal to 1, it will go to the first element in the list. That is 2, and 2 is not equal to 1. So increment I by 1, it will move to I is equal to 2. Now compare 9 with 1, it is not there. Then again increment I by 1, it will be equal to I is equal to 3. Then 3 is not again equal to 1. Then move to index number 4 and match the number to be searched. So I is found at 1 is equal to 1, and I is found at index number 4. This is how linear search is done. This we have implemented in the lab. Algorithm linear search. For I is equal to 1 to last index, we have to traverse each and every element of the array, right from the starting index from 0 to last index. Then if ai element at the index of A equals the element which we want to find, then it will say return I, else return -1. -1 stands for not found. So this is the linear search. And what could be its analysis? We have three cases already explained to you. First is the best case, second is average case, and worst case. So best case is minimum comparisons, whatever are required. So that means if you are looking for 2, it could be in the first position, fine, or that is called your best case. And if it is somewhere after the first position and before the last position, this is called average case. And for the last position, it is called the worst case. When you find a given number at the last position, then it is called worst case. See, this is how the descriptive analysis is done. In case 1, element 2, which is found at the first position. So minimum number of comparisons are required. So this is called best case. Now element 3 anywhere after the first position. So the average number of comparison are required. That means anywhere after the first position and before the last position, which is being described by the pink line over here. This is called average case. And worst case, when see in case of element 7, if we're looking for element 7 and it is at the last position, or element is not found at all, then maximum number of comparisons would be required. So this is called worst case comparison. This is the analysis which is done. In best case, resource usage is minimum and algorithm is behaving under optimal condition. Optimal condition means the best condition, means we have found algorithm is already in the sorted manner. So we have no problem. We faced no problem we made no comparisons. We faced no problem in finding the particular number from the given list. Now, in best case, minimum number of steps would be required or minimum number of comparisons would be required. So that means minimum number of operations we have performed. So this is the lower bound on the running time. Whenever minimum comparisons are made, that means it will take minimum time. So that is called lower bound on the running time. Now, average case, resource usage is average. Then algorithm behavior is random because we are going to find the number anywhere after the first position and before the last position. For that, we require average number of steps or the operations which are to be performed. So definitely your number will lie between the lower bound and the upper bound. So when the number lies between the lower bound and the upper bound, it becomes the average bound. That means average number of comparisons we have made and it lies between the lower bound and upper bound. That we will see when we will implement the asymptotic notations. Then worst case, resource usage is maximum. Algorithm behavior under is worst condition because we are making the maximum number of comparisons because either the element is at the last position or it is not existing in the given array at all. So we will have to find and maximum number of operations we have to do. That means what will be the maximum time that will be taken by the algorithm to execute is called the upper bound on the running time. So best case generally do not occur in reality. Whenever we are facing the physical world, they do not occur. Generally, average case and worst case analysis are preferred and they are mostly used in algorithm analysis because we are always concerned about the maximum time in which the operation can be performed. We are never bothered with the least time. We are always bothered with the maximum time or the worst time that could be taken by an algorithm to get executed. So this is your book finder example. You have been given so many books. So suppose we are writing a program to find a book from the shelf. From any book required, we'll start checking the books one by one. We want Harry Potter 3. So it will take only 3 actions because it is the third book. Fine. Then 7, it would be the last book. But if there are 10 books, then if it would have been 1 million books, then we have to take 1 million tries, right? So this is again the number sorting example. So number are already in sorted order. So that is the best case. Numbers are randomly arranged. That would be the average case. Numbers are arranged in descending or decreasing order. That would be the worst case because here we have to perform the maximum number of comparisons in order to bring it to the increasing order. Fine. Whenever you are sorting any number, you have to bring the numbers into the increasing order or ascending order. If they are already in increasing or ascending orders, then it means best case. But when the numbers are randomly arranged, that means they will keep on changing their position, then it is called average case. When the numbers are arranged in descending or decreasing order, it is called worst case because we have to make the maximum number of comparisons. So next is your number sorting that we have done. See again the description about it. Suppose you are sorting the numbers in ascending or increasing order. The initial arrangement of the given numbers can be in the following orders. First, numbers are already in the required order, that is ascending order. No change is required, so that is called best case. Numbers are randomly arranged initially. Some numbers will change their position during the, bringing them into the increasing order. So this is called average case. And in case 3, the numbers are initially arranged in descending order. So all the numbers are going to change their position right from the first number to the last number. So that is called worst case. So sorting, this is the actually summary. What 3 problems we have done? First is linear search. The element is found at very first position. In average case, the element is anywhere after the first and before the last. And in worst case, the element is at last position and is not present at all. In book finder case, the first best case would be the first book. Average case, the book would be in the middle, and worst case, it would be the last book. Then sorting, the elements are already sorted in case of best case, and we will not make many comparisons. In average case, the elements would be randomly arranged, and in worst case, it would be reversed order or in decreasing manner. So this we will do later on. First of all, we will complete our asymptotic notations part. See, yesterday we did big O notation, that is the worst case complexity. Today we'll be doing big omega. See, big omega is used to find the lower bound. Lower bound means minimum number of comparisons to be done. And this will be your best case because minimum number of comparisons are always done in the case of best case, because we did big O, that is used to find the worst case. That means if this is my function fn, we have to trace out a function gn which could be always less than this fn. Fn should be always be greater than C of G of n. That means C of G of n will always be smaller than f of n, which implies that will always be smaller than f of n. That means you have to find the tightest lower bound. For example, 3n plus 2 should be greater than 3 of C of n, C of G of n, where n is my n and c is any constant value which is going to be multiplied. So 3n plus 2, if I substitute 1 for c, substitute c as 1 and n as 1. So c will be 1 and n will be 1. So 3n plus 2 is going to be greater than 1. Okay. Similarly, if I put 2, then 3n plus 2 is also greater than 2n, and 3n plus 2 will always be greater than 3n. But if I say 3n plus 2 greater than for 4n, no, because 4n is going to be greater than 3n plus 2. So this equation will not hold. That means the values right from 3n up till 1n, this equation will hold. So the tightest bound for this equation would be 3n plus 2 is greater than 3n. So 3n would be the closest bound for this equation. Fine. Similarly, if I write here 6n plus 6, and we have to prove that we should be equal than C of G of n. Fine. And Gn is given us as n. 6n plus 6 would be greater than equal to 6n. You can take the same thing here. Fine. So, but if it becomes 7n, then this equation will not hold. So don't write it like this. You have to go for 6n because this is the tightest bound. Although this equation is also holding for 5n, 4n, 3n, 2n and n. Okay. So this is called the lower bound, which we'll be able to find by using this. For certain n, which is greater than or equal to n naught, or n naught is equal to 1, and for certain constant which is going to be greater than 0. This is the lowest bound which we are going to find. Now we will start with the big theta. That is called average case complexity. Average number of comparisons we have to find. That means my graph would be something like that. This is time and this is n inputs. So if I write here as C1 of G1, Gn, this is my lower bound, this is my function, and I will write C2 of Gn, that is my upper bound. Fine. So there is one, okay. Same equation is there. We have to find 3n plus 2 is equal to theta of n. Okay. For that, your condition is generally this: C1 and G1 should be less than Fn, and Fn is less than C2 of G2 of n. Now, how you will say this? This is my lower bound. So lower bound is always less than my main function, and my upper bound will always be greater than my Fn. Fine. So Fn lies in between C1 and C2. C1 is less than Fn and C2 is greater than Fn. So if I find the upper bound for 3n plus 2, it would be 4n because we have already done this. And here it would be 3n. That means closest bound for 3n plus 2 would be 3n, and tightest bound is upper bound will be 4n. So average case complexity, that is Cn would be 3n plus 2 is theta of n for C1 is equal to 3 and C2 is equal to 4 and n is equal to 1. This condition will hold. If you substitute the value of n here, 3 is less than 3 plus 2, 5. 5 is less than 4 into 1, that is 4n. If I substitute, that means, just wait. But here we have to increase this as 5n because it is not going to be less than 4n. So this would be the tightest bound where this relation will hold. For C1 is equal to 3 and for C2 is equal to 5 and for n is equal to 1, this relation will hold. Now if I substitute the value of n as 2, then what happens? C1 remain 3, C2 will, let's substitute value as 2. 3 into 2, I'm taking this relation. 3n is less than. So for n is equal to 2, 3 2s are 6, which is less than 8, and it is less than equal to this. That means this relation will hold for C1 is equal to 3, C2 is equal to 4, and n is equal to 2. So the average case complexity will hold, that is 3n plus 2 is theta of n for C1 is equal to 3, C2 is equal to 4 and n is equal to 2. First of all, you have to find the constant values, then you will substitute the values of n to find the relation. This could be your answer, but it is for n is equal to 1. But when we are bringing it in the terms of the closest bound, then it would be 3 into 2, that is, C1 would be 3 and C2 would be 4 and your n would be 2. So we can have more examples of this. So let's do this. One more example. You have to find 2n plus 3 is a theta of n. Now you will write 2 into n is less than 2n plus 3 is less than 3n. So for which value this relation is going to be satisfied? Let's do it for n is equal to 1. 2 into 1, 2 into 1 plus 3 is less than 3 into 1. So 2 into 1 is 2, and this is 5, and this is 3. So this relation is not holding. Leave it. Now comes the n of 2. So 2 into 2, 4. 4 is less than 5. Sorry. 2 into 2 plus 3, that is 7. And less than 3 into 2, that is 6. So 4 is less than 7 and it is less than 6. Condition false. So it is not satisfying. Now let's come to n is equal to 3. 2 into 3, 6, which is less than 6 plus 3 is 9. Okay. Then you'll write 3 into 3. So 3 into 3 is 9. So that means this relation is okay. And it is theta of n for C1 is equal to 2, C2 is equal to 3, and n is equal to 3 onwards. This is how you will find the big theta of the equation 2n plus 3. Now let's find the upper bound for the same and lower bound for the same. Now let's find the upper bound for the same. Upper bound is big O of n. What do big O of n says? That Fn is smaller than C of G of n. Okay, so we have been given 2n plus 3 is less than n. Okay, now for what value of C it would be less than n? Let's substitute C as 1. So 2n plus is less than 3n because that would be the closest bound. And for which value of n it is going to be satisfied? 2 plus 1 plus 3 is less than 3 into 1. So this is going to be 5. 5 is less than 3. No. So substitute n is equal to 2. So 5, 2 into 2 plus 3 is less than 3 into 2. So 2 into 2, 4. 4 plus 3, 7 is not less than 6. So let's do it for n is equal to 3. 2 into 3 plus 3 is less than 3 into 3. So 2 into 3 would be 6. 6 plus 3 is 9. And 9 is less than 9, equal to 9. So that means for n is equal to 3 and C is equal to 3, this relation is going to be whole. So that means this would be big O of n for C is equal to 3 and n is equal to 3. This is how you will do. Similarly, if I want to find the omega of n, then this condition will reverse. This condition will reverse. 2n plus 3 is greater than 2n. Now for which value of these values are going to be satisfied? For n is equal to 1, 2 into 1 plus 3 is greater than 2. That means 5 is greater than 2. That means Fn is big omega of n for n is equal to 1 and C is equal to 2. I again repeat, Fn is big omega of n for n is equal to 1 and C is equal to 2. Now let's do it for 7n plus 5. It is equal to, we have to find it is big of n. 7n plus 5 is theta of n. 7 plus 5 is omega of n. This is the problem which is given to us. So for big O, that means my Fn is smaller than C of G of n, that is big O of n. So Fn is 7n plus 5 and it should be less than C of n. That is 7n plus 5 is less than 7n. Now for which values of n it is going to satisfy? Let us do it. For n is equal to 1, 7 plus 5 is 12. 12 is not less than 7. Now for n is equal to 2, 7 into 2, 14 plus 5 is 19, and it is not less than equal to 14. For n is equal to 3, 7 threes are 21. So what we are supposed to do? Okay, we have to do it here 8n. 8n. I have taken the lower bound. We have to take the upper bound. So this could be 8. 12 is not less than 8. It is okay. Now let's do it for n is equal to 2. It becomes 16. So it is not less than 16. Now let's do it for 8 into 3. That is 24. 21 plus 5 is 26. It's not going to be there.
N
Then
equal to 4, ma'am.
Yes. 8 into 4, it would be 32. 7 fours are 28 plus 5, 33. It is not going for satisfying for n is equal to 4. 7n plus 5 is less than equal to 8 into 5, that is 40. 7 into 5, 35 plus 5 is 40. So it is going to satisfy for n is equal to 5. Fine. So for c is equal to 8 and n is equal to 5, this equation is going to be satisfied. I again repeat, we have to take the upper bound here because it is less than. So we are going to take the upper bound 8n. So n is equal to 1. 7 plus 5 is less than equal to 8 because n is 1. So 12 is less than 8. Not true. Then here n is equal to 2. 14 plus 5 is 19. 19 is not less than 16. So this condition does not hold. Then n is equal to 3. 7 into 3 plus 5 is 26 and it is less than 24. Then we have 7 into 4 plus 5 for n is equal to 4, which is equal to 33, and 8 into 4 is 32. Here 7n plus 5 is less than equal to 8 into 5. So 8 into 5 is 40. 35 plus 5 is 40. 40 is less than 40. So for n is equal to 5 onwards, this relation will hold. Okay. Now let us do it for
It will be the lower bound, ma'am.
which one? That would be the upper bound, beta. What we have found is big O of n. According to big O of n, my function is there, and my your C of G of n should be greater than Fn. That means Fn should be smaller than C of G of n.
Oh,
Okay.
okay, ma'am. Okay, ma'am.
Now lower bound we have to find is, that means C of G of n should be less than F of n. That means F of n should be greater than C of G of n. That means what? F of n is 7n plus 5 and it should be greater than 7 of n. Fine. So substitute n is equal to 1, you will get 7 plus 5, 12, which is greater than 7. For n is equal to 1 and c is equal to 7, you will get this answer. Okay. For n is equal to 1 and c is equal to 7, this relation will hold for values of n above 1. Actually, here what we are trying to find is this n naught. What will be the n naught value for which this relation will hold? Fine. We will find the value of that n naught for which these relations will hold. Fine. Now we have to find the theta. Now we have found the 8n. That is big O. You have found as 8n. Now you are finding the this is big omega. So your theta will lie between 7n plus 5 is less than equal to 7n. Fine. Okay. Just wait. 7n is less than this. This will be the answer. For average case complexity, this is average. This is my best case and this is my worst case. So you have found the big omega. It lies theta. Then we have big O. So 7n is my best case. 7n plus 5 is theta and it lies between 8n. Now for this, your C1 is 7 and N1 is 1. For here, what would be the answer? What we have drawn? C2 was 8 and N was
5.
5. See, if I substitute 5 here also, then 7 5s are 35. This becomes 40 and this becomes 40. Then this also relation holds. That means we can consider this relation will hold for C1 is equal to 7, C2 is equal to 8 and N is equal to 5. Okay, because this is 7 into 5, 35. 7 into 5 plus 5 is 40. Then 8n is 8 into 5, that is again 40. So that means 35 is less than 40 and it is less than 40. That means C1 is 7 and C2 is 8 for N is equal to 5 also holds. So next thing is how to analyze the control statements. How you will analyze the control statements. See, we have been given to the algorithm to find the sum of arrays, the sum of numbers in an array. So for that, this is the logic. This everybody's know. Integer s is equal to 0 for I is equal to 0. I is less than n and I plus plus. So s is equal to s plus ai. See, first loop, as you can see, the figure is there. It is saying with n plus 1. That means this loop will go for n plus 1 times. Why? Because you are starting the loop from 0 and once, no doubt, if it will have 10 elements, it will actually add the 10 numbers. But 11th time, it will also check the condition whether 10 is less than 10 or not. It is not less than, that means the condition becomes false. Whereas the statement which is inside the for loop, that is s plus ai, will be running for n times. So return s will also be running for 1 unit of time. So I can see that we can say that n plus 1 plus n plus 2. Fine, because s0 is also one statement. For that one is there and return s for that one is there. That's why it is n plus 1 plus n plus 2. And when you make the total, it becomes, when you add all these numbers, it comes out to be 2n plus 3. So that means complexity is 2n plus 3. I can explain it in the board. Just wait. I'll show you how this works. See, what is the code? Integer s is equal to 0. I won't write the algorithm statement here. So for I is equal to 0, I less than n, I plus plus, then sum is equal to sum plus ai, and then we will say return s. See what happens. This will take 1 unit of time. This will take 1 unit of time. How many times this statement will be executed? Because before completing the asymptotic mutations, I told you that we have to see how many times each statement is being executed. See, for that, if I say this array has 10 numbers, 11th time it will check whether 10 is less than 10. If condition is false, then it won't enter this loop. So that means this will execute for n plus 1 times. And the loop and the statement which is inside the for loop, that is this statement, it will, because at 10th time this loop is going to become false. So this will work only for n times. If you add up all these, you will get n plus 1, 1 for this and 1 for this. So this becomes 2n plus 3. Okay. And highest power of n is 1. So this is fn of n. We can write this function is fn is big O of n, because your power is n. Okay, your power, maximum power of n is 1, so this big O of n. Similarly, if we are having two loops here, for example, for j is equal to 0, j less than n, j plus plus. So this will be, suppose s is equal to s plus aij. That is we do in the case of matrices. You may write here like this. I'm just taking it as an example. See, this will be uh, n into n plus 1. This loop will go for n1, n plus 1 time. Since this loop is inside the major loop, so this will work for n, and it will also run for n plus 1 times because it is also having this statement. So this would be running n times. Now, if I see n plus 1 plus n square plus n plus n, it comes out to be n square plus 3n plus 1. It comes out to be n plus 1, n square plus n plus n, n square plus 3n plus 1. So highest degree is n is 2. Highest power of n is 2. So highest power of n is 2. So it becomes fn is equal to big O of n square. See, this statement will run for n plus 1 times. Since this statement is enclosed inside this loop, so it will work for n times. And for itself, it has to run for n plus 1 times because this is a loop which is also checking the condition of n. Then this is a statement which will be working for n times. When you add up all these, you will get n plus 1 for the first statement. Then you will get n plus n into n plus 1. Then you will get n. So n plus 1 plus n square plus n plus n. 1, 2, 3 n are there. So you will get n square plus 3n plus 1. So highest power of n is 2. So this is fn is O of n square. This is how it is done. Okay. Okay. So we will be doing these analysis of control statements in the next lecture. So thank you so much. And if you have any queries, you can WhatsApp me personally, or you can send me the screenshot. We can solve it.